Hello and welcome back. Today we are going to look at the refrigeration cycle, what is also called as the vapor compression refrigeration system cycle or VCRS. All of you have seen a refrigerator. If you have looked at refrigerators which have the back open in some form, so you must have seen it looks something like this. So it has a compressor which is used to compress a refrigerant. It has this heat exchanger over here, this black thing, what we call as condenser. And so what we see is from the compressor, the liquid, high pressure liquid refrigerant goes in this pipe and goes into this condenser, where it condenses and forms a liquid. The liquid from this condenser exits through a filter and goes into this capillary tube or an expansion valve, and from there it goes into the refrigerator where it cools the stuff which you want to cool inside the refrigerator, and then finally it comes back and goes into this compressor where it is once again compressed. So if we were to look at this on a sort of a schematic, what we see is we have components of this kind. We have a compressor where we take in refrigerant, we compress it, it becomes high pressure refrigerant. The temperature increases while we compress. Ideally, we would like to compress this isentropically, reversibly and adiabatically. And after compressing, we are left with high pressure refrigerant. This refrigerant then goes into a condenser where we allow it to reject latent heat and become a liquid. So it is still at high pressure, it rejects heat, becomes a liquid. This liquid is something which we usually send through an expansion valve or a throttle valve. In this process, the pressure of the refrigerant reduces. This refrigerant is liquid when it enters this expansion valve. It is not an ideal gas in by any means. As its pressure drops in the expansion valve, what we see is that its temperature drops, its quality increases, it starts to become vapor, and then we are left over here with a mixture of liquid and vapor which we send through the evaporator. This mixture is cold. In the evaporator, it takes heat from whatever substance you want to cool, and then you are left with hopefully saturated vapor, which then you can send into this compressor. So this is essentially how this works. So we have work input given in the compressor, we have heat transferred out in the condenser, we have heat transferred into the evaporator, and then we have the expansion valve, which is a throttling process. We have discussed earlier that the throttling process ideally would be adiabatic. It is highly irreversible. There is no work done in this case. So we can look at this process on a TS diagram, but what we can also do is see why we use this process at all or the cycle at all. So if we were to look at our ideal refrigeration system, the ideal refrigeration system would be a Carnot cycle running in reverse. So which by running in reverse, what we mean is that heat is transferred out of the cycle at high temperature and heat is transferred into the cycle at low temperature. So 2 to 3 is a process of heat rejection. This should be at higher temperature, and 4 to 1 is a process of heat addition to the cycle. It should be at low temperature. So which essentially means that the cycle runs anti-clockwise as compared to our power generation cycles which run clockwise on a TS or a PV diagram. So ideally we would like this cycle, but as we discussed earlier, it is hard to have processes 1 to 4, 4 to 1 and 2 to 3 as isothermal heat addition and heat rejection when we are using single phase flow. What is easier to do is to do constant pressure heat addition or constant pressure heat rejection. And one of the ways in which we can achieve both a constant pressure and a constant temperature process is to put this into a liquid vapor dome. to use two-phase flows. So that is essentially what we do, like in the other cases. We do this with a two-phase mixture, because then a constant pressure process is the same as a constant temperature process, and constant pressure processes are something which we can achieve. So this is a modification which we would first do. Instead of using a single phase substance, we could do this in a two-phase mixture and then run what would be a Carnot cycle. But as we saw in the case of, say, the Rankine cycle, we also have problems here, because once we have a two-phase mixture, now we are trying to compress a mixture of liquid and vapor. Because if I want this entire cycle to be in the dome should pass through these points 2 and 3, or it should be smaller. And in that case, what I am compressing here, 1 to 2 is compression. Ideally, it should be isentropic compression, reversible adiabatic compression. But in this process 1 to 2, I am trying to compress a mixture of liquid and vapor at 1 and get only vapor at 2. It is difficult to find compressors which can deal with two-phase mixtures and do this efficiently and do this without getting damaged. So what we would like to ideally do is to make sure that in the compressor there is only a single phase. So which means that we should do all compression either in liquid, which does not help us, because in that case the entire cycle is going to be in the liquid, or we can do the compression in the vapor phase. So here we have liquid, here we have vapor, here we have a two-phase mixture which we represent as 2phi. So what we would like to do is to move this compression out of this mixture. So one way of to do that is to essentially move this point 1 to the saturated vapor line and then compress from here. This will still be isentropic compression, so it will be a straight line parallel to the t-axis. We can compress like this. So if we compress up to this temperature 2 to 3, and if we wanted to do this, then what we would see is this portion, the dotted region, would essentially be isothermal compression. The process from 2 to 3 is isothermal, but more importantly it is constant pressure heat rejection. But this portion, the dotted portion, would be isothermal heat rejection, which is difficult to achieve. So this is not very feasible. So what is feasible is to make the heat rejection process, which is essentially this portion as well as this portion, make those at the same pressure. So we can draw this isobar, which is the isobar is essentially this line. That is what an isobar looks like on the TS diagram. So what we are trying to do is make use of that isobar. So instead of compressing to the pressure at this point, we compress to the pressure at 3. So if the isobar at 3 over here passes through this point, so what we see is this 3, and let me call this point as some A, and this point as some, this point is 2. So this pressure at 3A and 2 is the same. So in order to reach that pressure, what we need to do is we need to compress to a higher temperature in the vapor region. The pressure is still the same at 3 and at A and at 2, because this is an isobar, but the temperature is different when you are in the vapor region, when you are in the two-phase region, and let us say some point over here in the liquid region. The pressure is different in the, the pressure is the same, but the temperature is different at different points in this region. So we are now left with this cycle, which starts at saturated vapor, dry saturated vapor at point 1. We are compressing to some temperature T2, the pressure at 2A and 3 are the same. Then we can do constant pressure heat rejection in a heat exchanger from 2 to 3. This heat exchanger is a heat exchanger where we have vapor becoming liquid. So the process is happening by condensation. So we call this heat exchanger as a condenser, and we are left with liquid at point 3. Now 3 to 4 is an expansion process, In the Carnot cycle, this would be a reversible adiabatic expansion or isentropic expansion. We would ideally do this in a turbine. But we have seen issues with using a turbine in two-phase mixtures earlier. So, again we are starting with liquid at 3. At 0.4 we are in between the liquid line and the vapor line, which means it is a mixture of liquid and vapor. So, we are going to have problems with liquid droplets hitting the blades and damaging the blades. That is one potential problem which we would have. But there is also another issue. So, we saw that the work in the turbine would be given as the specific work would be essentially the change in the enthalpy between the inlet and the outlet, assuming that there is no change in potential and kinetic energy, and assuming that this is adiabatic and it's steady state, this would be the kind of work we get. And we saw that for an isentropic process, we can also write this as integral of V dP. And what we see over here is we are close to the liquid line. So, if we are close to the liquid line, then the specific volume is small. The specific volume of vapors is very high, the specific volume of liquids are small because the density of liquids are large. So, even when we are at 0.4, we are closer to the liquid line than to the vapor line, which means that the specific volume will be small. So, the amount of work we can get by putting this turbine here is fairly small. A turbine is an expensive device. We want to, for example, manufacture a fridge and sell it. So, let us say a fridge costs something like say 10,000 rupees or something like that, or say 15,000 rupees. If we make a turbine, it would be very expensive. So, it would increase the price of the fridge by a large amount, and we will not get much work because specific volume is small, and the turbine would possibly get damaged because it is dealing with two-phase mixtures. So, all of these leads us to the conclusion that putting a turbine here, even though it is useful to improve the efficiency of the cycle, it is possibly not going to be very feasible from a cost perspective and from durability of this device. So, what we usually do is we remove the turbine and we put a throttling device. A throttling device can be essentially a valve. It can also just be a tube with very small diameter. So, we put a throttling device. So, for example, if you have liquid coming at 0.3 and then you make it pass through a long tube whose diameter is very small, there will be a lot of pressure losses in this tube because of friction. So, typically this tube is extremely long and you can coil it around. Of course, you would possibly have the same diameter. I have not drawn it all that well, but what we see is when this liquid flows in through this tube, it has viscosity. So, it has a lot of pressure drop. So, the pressure drops in this case. If this flows fast, we can assume that this process happens adiabatically. So, it is adiabatic, but the pressure is dropping, and in this process what we see is that the enthalpy remains constant. If we if we assume this to be steady state and if we ignore changes in potential and kinetic energy, then the enthalpy remains constant and the pressure drops. And for non-ideal gas substances, if you choose the range of initial temperatures correctly, what you would have is usually a temperature drop. Of course, the actual case of whether the temperature will drop or increase depends on the Joule-Thomson coefficient, but we are in if you are looking at a gas, it could either increase or reduce. In the case of these kind of mixtures which we have here, in the case of liquids of the kind we have here, in this condition the temperature would drop as the pressure drops. So, what we see is at 3 the temperature is T3, at the exit of this at 4 the temperature drops from T3 to T4. This is an irreversible process because there is friction, which means that the entropy increases. So, the entropy increases and the temperature drops. So, 0.4, the temperature at 4 should be lower, the entropy at 4 should be higher. So, this is the entropy at 3, entropy at 4 should be higher, and this is now an irreversible process. So, we do not know what this shape of this process is. So, but we are left with now a cycle of this form. So, we started with the Carnot cycle. We can modify that into the reverse Rankine cycle by doing this kind of compression here in the vapor region and having a turbine here. But then that is not very useful either, because the turbine is expensive and it has problems. So, what we have now done is we have changed it into an isenthalpic process, which is irreversible, and we are now left with the vapor compression refrigeration system. Which is called VCRS in short, which gives us this cycle. So, the same cycle is drawn over here. So, we have 1 to 2, which is isentropic compression, 2 to 3, which is constant pressure heat rejection out of this cycle, which is usually heat rejected to the atmosphere, 3 to 4, which is a throttling process, which is adiabatic and irreversible, 4 to 1, which is constant pressure as well as constant temperature, heat absorption, where we are taking heat from the substance which we want to cool and taking it into the cycle. And then 1 to 2 once again is reversible adiabatic compression. So, this is essentially the VCRS cycle, which we use instead of the Carnot cycle. So, we can look at what are the things which we are doing in this cycle. So, we have heat rejection here, QH, we have heat absorption into the cycle, which is QL, which is usually what we are interested in if we are running this as a refrigerator. If we are running this as a heat pump, we would be interested in this QH. This 3 to 4 is a throttling process. There is no heat transfer in this throttling process. We also do not have work done because there are no moving parts, there is no shaft, there is no change in the cross section of the, there is no change, not in the cross section, there is no change in the volume of the device in which it happens. So, we do not have heat transfer here, we do not have work interaction here. Over here we are doing work on the system. So, this would be compressor work, which would be negative for this cycle. QL is positive for the cycle, heat coming in, QH is negative for the cycle, it is heat going out, and here we do not have heat or work transfers. So, if you want to find out the amount of heat coming in over here, sorry, the amount of work coming in over here, this is isentropic, there is no heat interaction here. What we have been typically doing is drawing this as some kind of a system of this kind. This is WC, this is QH, this is QL. So, from the first law, this is running as a refrigerator. We have been usually maybe putting the other kind of arrow, I do not know, maybe anti-clockwise to show that this cycle is anti-clockwise here maybe. So, this is positive, this is negative, this is negative, that is one of the things. And from the first law for a cycle, we have sigma q equal to sigma w, which says that WC is equal to QH plus QL. This is negative, this is negative, this is positive. So, I would have a negative value here, a negative value here and positive value here, knowing that these two are negative and this is positive. And what I can do is take mod of this and to find out the positive value, which is essentially the positive value of QH, the magnitudes, difference in the magnitudes, because what I know is if I take only the magnitudes, QL is going here, WC is going here, both these should be added up in magnitude to give me QH. So, this is like these two adding up and giving this, because the arrows are like that. So, that is essentially what I should get. So, if I was to write the first law for the compressor, so if I was to look at only the compressor, so the general form of the first law, the compressor can be treated as a control volume where there is some mass coming in at 1, going out at 2. So, first law for the compressor would give me this. There is only one inlet and one outlet, I do not need a sigma here. This is the first law. In addition, we have conservation of mass, which is dm by dt is m dot I minus m dot E. If it is at steady state, this is 0 and m dot I is equal to m dot E, and I can call these as some m dot. So, I can remove the subscripts. If it is steady state, this is 0. For the compressor, we expect this to be isentropic. So, there is adiabatic and reversible, this is 0. So, I can divide this W dot by m dot and call this as some small w. Changes in potential and kinetic energy are usually small. So, these are 0. So, what I see is W dot is equal to m dot into inlet enthalpy minus exit enthalpy. So, if I was to write it in terms of capital W, I need an m dot over here, or if I was to write it in terms of small w, I see this is inlet enthalpy minus exit enthalpy for this compressor. From the first law, this should also be equal to, from the first law for a cyclic process, this should also be equal to QH minus QL in terms of magnitudes. Of course, QL is anyway positive, so I do not need the mod sign here, but anyway. Now, in a similar fashion, we have found out how much would be the heat transferred. So, in the case of say 4 to 1, it is a steady process, this is 0. There is no work done because in 4 to 1 happens in a heat exchanger. There is only flow work which is already taken into account in the enthalpy. There is no displacement work, there is no shaft work, no electrical magnetic work and so on. So, for the heat exchanger this is 0. Changes in potential energy and kinetic energy are small, it is a steady process. So, Q would be m dot into enthalpy at the exit minus enthalpy at the inlet. So, this is m dot into enthalpy, in this case it is enthalpy at the exit minus enthalpy at inlet. In this case it is enthalpy at exit is 1, inlet is this will be m dot into this, or small QH would be H3 minus H2 and small QL, which is specific heat transferred, would be this, and COP is defined as what we want. For a refrigerator, what we want is the amount of heat we can remove from here, which is QL, and what we need to give is work in order to run this refrigerator. So, for a refrigerator, the COP would be QL by WC, and if it was a heat pump, what we are interested in is how much heat we can get from here to heat a room. So, we would be interested in QH, and what we need to give is WC. So, that is essentially what we see. And for the throttling process, we can also write what we get. For the throttling process, it is still a steady process. So, dE by dt is 0. The throttling happens in an insulated tube. So, Q dot is 0. In this tube, there is no change in the volume of the tube itself. There is no PDV kind of work. There is no expansion of the tube. So, that is not there. There is no shaft in the tube. There is no electrical or magnetic work in the tube. So, any forms of work are 0. If I can ignore changes in potential and kinetic energy, then these are 0. M dot is constant, I can take this to the other side. So, what I am left with for the throttling process is that enthalpy at the inlet is equal to enthalpy at the exit. So, in this throttling process 3 to 4, what we see is ideally Q dot is 0, W dot is 0. Ideally Q dot is 0 because I am assuming adiabatic. W dot is 0 because there is no way in which it can do work, and enthalpy change is 0. So, there is no, because inlet enthalpy equal to exit enthalpy, enthalpy change is also equal to 0. What changes here is pressure changes and temperature changes in this throttling process. So, that is essentially what we have for this VCRS cycle, which is used for a refrigerator or an air conditioner and so on, or a heat pump. So, we are going to stop here for the moment, and we will go on to a problem which deals with a refrigeration cycle. Thank you.